Stapler,
I don't have a stapler, but if you want, you can initial your pages and that should be just fine.
I'll do that.
I really need to invest in a stapler. I'm gonna make that a project and thing.
For you,
Thanks.
the last one,
Kind of nasty.
that was nasty, yeah, that probably got me.
Yeah, I got a lot of questions on that one. Okay, I'm just putting down a note that says invest in a stapler. Okay, we might have a better quality of life going forward with homework. I'll try to have a classroom stapler that I'll bring. Well, welcome back, everyone. Today's class, we're just finishing off section 3.7. Any extra time we have, I'll probably turn to just homework hints for the actual homework assignment down below. Some of them are more trickier than others. But before we start any of that, were there questions or things folks would like to start us off with? Okay, let's dive right in then. So in section 3.7, we're dealing with rates of change in the natural and social sciences, or derivatives in applied settings is another way you could say that. We finished up our first example and our third example below because it was a little bit shorter. That saved this one just so we can make sure we had enough time to do it in completion. So here's what's going on in this setting. It says the number of yeast cells in a laboratory culture increases rapidly, but levels off eventually. So N looks like it's the number of yeast cells in that culture. The population is modeled, so population size, by this function. It's written in kind of a strange way. It goes N first for the dependent variable. If you want to use function notation, you could also just call it f of t overall. But putting this in is also helpful because it's telling us that the independent variable inside that function, let's blow it up a bit, is that variable t right here. Well, it's kind of hard to select that variable t right around there. So that's the function that's going to model the number of the yeast cells. Here it says t is measured in hours. Our constants a, b are positive. So that's a and b here. We know they're constant because f of t implies the independent variable is t. And they also tell us at time 0, the population is 20 cells and is increasing at a rate of 12 cells per hour. Then part A, not giving us much guidance at all, just says find the values of A and B. That's a really tough one to even start, right? But the best way to start this question is going back to this statement right here. They gave us really two kinds of function outputs. At time 0, the population is 20 cells. Let's write down an equation for that. Here, they're not talking about the derivative or anything. They're talking about the population size. I'll use the dependent variable n, but if you decide to use function notation, you'd say f of 0 equals 20. Instead, I'll write at t equals 0 hours, n is going to be equal to 20 cells. Each cells, I'll just call them cells for short. Then they say, and at the same time, 0 hours, it is increasing at a rate of 12 cells per hour. I would say this is the huge, huge buzzword in that entire portion of that sentence. When they said rate, they're not talking about a derivative. So the rate of change of the yeast cells with respect to time was, if they gave us mixed units as a rate like this, they're probably talking about a derivative as well. So really the key to this problem is to know that first portion was just a function output, but this portion, increasing at a rate of 12 cells per hour, somehow I'm not able to highlight that. Let me grab that. Sorry, I'm having trouble with Microsoft all of a sudden. I'll just do it this way. This right here is the derivative. So let's take that and write the rate of change of the number of cells with respect to time when time is equal to 0 hours came out at 12 cells per hour. So that's our entire statement of the question? Well, the second sentence here, we broke it down now into two equations. N is 20, and the derivative of n with respect to time is 12 cells per hour, all at the initial time. Any questions at that stage so far, folks? Okay, I would say with what we wrote down on paper right here and right here, this is really the biggest takeaway of section 3.7. If we see information written in this kind of form, if you can tell which one is a function output, which one is a derivative, you're doing really, really great in this section. It's tricky, so that's why we're practicing it. Well, if we have two equations, well, it seems possible to solve for two different values with two equations. So let's maybe start with the easy one. The low-hanging fruit is the one where we don't have to take the derivative of anything. In place of n, let's just put in the entire function that we see on the right-hand side. It'll be a divided by 1 plus b e to the power of negative 0.7 t. So that's the left-hand side where n was, and we'll equate it to 20. Oh, I did make one mistake. The 20 is okay there, but my mistake is, don't forget this is at time equals 0 hours. I need to plug that 0 right here when I go to put in that left-hand side. Sorry for anyone working in pen today. That should be times 0, which is a good thing. That simplifies the function. This is going to be a little bit nicer to work with. So at time is 0 hours, we can simplify the left-hand side and get a, so I want to keep this in blue, a divided by 1 plus b equals 20. So we have an equation here. It involves two unknowns, a and b, so I can't really do much with that. But you could at least solve for the value of a, multiply both sides by 1 plus b, and a is 20 times 1 plus b. Or if you prefer, a is equal to 20 plus 20b. Now, all we have to do is solve for b, and we'll have a at the same exact time. So that's pretty much the extent of what we can do on the left column here. We need now to turn over here and see how to work with this information. Any questions to this stage of the process? Okay, well, the trouble with this given information is it's a derivative evaluated at 0 hours, giving us 12 cells per hour, but we really can't do anything with that until we know what the actual derivative is. So first thing we need to do before we turn to that information in green is go back up here and take the first derivative of n, number of E cells. So let's calculate the rate of change of n with respect to time. There is really two good ways to do this. You can leave the function exactly the way it sits. You'd be using quotient rule potentially. Or if you wanted to, you could say that function is the same as a times 1 plus b e to the power of negative 0.7 t raised to the power of negative 1. So where the red dot is, that's quotient rule. If you decide to go this way, it's chain rule. Really, it's the same thing either way you do it. Just the quotient rule, you write out a big fraction. It just looks like it's more work. It's kind of the same process. Well, I'll leave it up to the class. Which one sounds funner, quotient rule or chain rule? Chain rule, let's give that a try. It definitely looks cleaner because you're not writing as much stuff. And I would only do this if you know your numerator is constant. If the numerator was a times t, I would just use the quotient rule. That's probably going to be the better approach. Okay, so we're going to focus on this form right here. If we do that, this function, the power negative 1 function, is the outer function. So we'll do that first. All the guts inside here is the inner function we'll handle second. And keep in mind, a is constant. So the first rule we actually use is the constant multiple rule. Here's how it goes. Nothing happened to a. So we did the constant multiple rule, it carries in. Next, we're differentiating the power negative 1 function. Negative 1 will come down. I'll later make that a negative a. The new power is 1 less, so now it's negative 2. Then we multiply by a derivative. Take everything inside here and put it in those two open spots. So 1 plus b e to the power of negative 0.7 t will go here. 1 plus b e to the negative 0.7t goes here as well. In this location, nothing happens, it's just copied. You can toss it down to the denominator. It might be a good idea since we're solving for things. Over here, though, we still have one more derivative to get through. So let's write down our next step. dn dt is now negative a I'm going to take this whole thing, put it in the denominator with the positive power of 2. So our standard trick, change the position, you just change the sign of the exponent. The 1 plus b e to the negative 0.7t will go here. Now this derivative, when we calculate it, I'm going to just multiply it up into this numerator. And here's what happens to it. We'll use the sum rule, take the derivative of a constant now, and we'll get a 0. Now next, here's the constant multiple rule. B is also a constant, multiplying, so it stays right in that position. And I keep on wanting the larger fraction. Let me extend that a bit more. But now when we get to here, we're differentiating that exponential. That's a chain rule. It just doesn't quite look like it. There's two functions really there. Let's zoom in on that just to really take a good look at it. In that setup where it's highlighted in yellow, what would you all call the inner function? Is it going to be e or is it going to be negative 0.7t? Exactly. That negative 0.7t went inside the e to the x function. So this one is inner. We'll do that one second. The outer function is that one. We'll differentiate the base e first. And here's what happens to this. We'll just take an e right here, put in a parenthesis, multiply by another parenthesis with a prime on there. So that's our next chain rule setup. Then take the inner function, function 2, and just copy it into those placeholders. So negative 0.7t, negative 0.7t goes in both of those locations. It's definitely kind of tricky because looking through this, when we went for this approach, it was chain rule to start, but then the derivative of this portion of the chain rule is yet another chain rule right here. Let's pause right at this location. I feel like a lot of stuff happened just on that one step right here. Any questions or comments at the moment? Okay, let's keep on running through it. This last derivative right here, not so bad. The derivative of negative 0.7t, just negative 0.7. So I'm going to take that negative 0.7 that survives, combine it with a negative a, and just call it a 0.7a. So at the moment we have, let's see here, it's going to be a 0.7a. It multiplies across 0, multiplies the b here, so it's 0.7ab. The function e to the negative 0.7t, still alive and kicking, survives in the numerator. And our full denominator is 1 plus b e to the negative 0.7t squared. So I think we've done it, folks. That's our derivative. I don't see how it can really simplify too much more. Any questions at all getting to that stage? Okay, I'm going to do something that looks a little bit weird, just because only because this problem is kind of a long one. I'm going to take the actual question and put it down here in case we have to refer back to it. Okay, let's keep on going then. So what we did at first was we had the original function n, we plugged time as 0, and we got that equation. But for this information, we had nothing to plug into. When we calculated dn dt, that's the thing we can now plug 0 into and get the rate of change equated to 12 cells per hour. So let's restate this equation here in green. dn dt, when t equals 0, is 12. All I did was drop units. Now that t equals 0 is going to be plugged in right here and right here. E to the power of 0 turns into a 1, so our function simplifies a whole bunch yet again. So now we have plug in 0, the numerator is going to be 0.7 times AB. The denominator is going to be equal to, well, it's just a 1 plus b squared. Yeah, go ahead.
Well, other than 0?
Yeah, that value right here by the red dot, the 0.
Oh,
That kind of looks like a weird number. Let me make that really look like a 0. Essentially, what was stopping us at first when they said t equals 0 up here was we didn't actually have the derivative to plug into. So now we take that 0, it's going here and here. So down below, it'll turn into a 1 plus b. This is now e to the power 0, so it's 1 again, leaving us just a 1 plus b squared. And the right-hand side I carried down is still a 12. So now the situation is we have two equations in two unknowns, but this looks like it should be solvable. It's not linear, so we might have to do something fancy. But the first thing I would do is eliminate that denominator. It's just easier to solve equations typically without denominators. So let's convert this to 0.7 AB equals 12 times 1 plus b quantity squared. Now, right here, we can also make a substitution. Recall that a is 20 plus 20b. We can plug that in right here for that a. So on the next line, it'll turn into 0.7 multiplied by a through substitution. It's 20 plus 20b. So we've done replacing a, b is still here, equals 12 times. You know, we might as well FOIL this right here now, since we'll eventually have to do it if we're solving for b. The expansion of 1 plus b squared is 1 plus 2b plus b squared after FOILing. So the equation is definitely cleaning up. We're going to distribute 0.7b through this group, collect all of our terms on one side, and decide how to solve that equation. Any questions or comments to this stage? Okay, let's do the distribution portion. My distribution here is always kind of weird. I'm going to distribute from both sides at once. 0.7 comes in and b comes in. So I'm just multiplying by 0.7b. 20 times 0.7 is going to come out as a 14. That turns into just a 14b on the first operation. Then here to here is going to give us plus 14b squared. So left-hand side is now taken care of. And we'll just redo that kind of thing on the right-hand side. Just distributing in from the left this time gives us 12 plus 24b plus 12b squared. So it turns into a degree 2 polynomial equation. Degree 2 is great because at worst, it's a quadratic formula. For a real exam question, I typically don't put quadratic formula questions on the exam. It just seems like not the best use of exam time. But something like this could be on an exam, maybe with nicer numbers. This one should factor nicely for us. Well, first thing we have to do is get all of the non-zero terms on one side. I'm going to bring them all to the left. So first thing I'm looking at is this 14b squared. Subtract 12b squared from both sides, and you'll get 2b squared. Next thing I'll look at is this 14b. Subtract 24b from both sides, and we'll get negative 14b. Finally, subtract 12 from both sides, and we'll have minus 12 equals 0. So that's our equation to solve. Before you factor that thing, though, you might want to cut it down to size. Oh, sorry, question first.
This is like 140 and 14.
Oh, probably not that, right? It should be negative 10b, right?
Yes.
Let me double check those numbers. I think that was definitely a mistake. Subtract 24 from 14, we get a nice negative 10. Thanks for spotting that there. I knew something was off based off the looks amongst the crowd, but I couldn't quite see what it was. Thanks for mentioning it. Other questions so far? Okay, well, this equation, again, you could factor it, but even this one, let's just divide the whole thing by 2. If you did that, you would get b squared minus 5b minus 6 equals 0. Then we can attempt to factor this thing. We can put a b here, and let's see, if it's a negative 6, our signs are mixed. It must go plus and minus. And if it's a -6, I'd want my 6 to have the negative and 1 to be associated with positive. Double checking, multiply here to here, that's -6b. Here to here is positive b, adding up to -5b. So I think we've got it, folks. We have two solutions. B is either -1 or it's +6. That already makes me uncomfortable. If there's two solutions, but we're told solve for A and B, that's kind of a weird situation. One of these actually does get eliminated. Anyone happen to know which one? Exactly. It's said at the very top. These are constants and they're only positive constants. So we can eliminate that -1 down below here. So this one's gone. I'll put a note. B is greater than 0. So we eliminated that. And we have a value. I'll put a box on this one since our work is spread out all over the place. But they told us solve for A and B, and that's our first solution. B has to be 6. Quite a process on this thing. But now if B is 6, we can just throw it up right there in place of A. So you now have a value for B, and we're about ready to finish off this first portion. A is now equal to 20 plus 20 times B, which evaluates to 6 once we solve this whole process. And so A turns into 20 plus 120. So finally, A must be equal to 140 altogether. We've got it, folks. That's the final portion of part A, solving for A and B. Let me bring, oh geez, I don't want to do that. Let me keep that right where it is. Okay, let me bring this up just for a moment. It's good to make a conclusion once you solve for A and B. My conclusion will be, therefore, N, number of yeast cells, is equal to, first we'll throw in the value for A, 140 in the numerator. Division by, down below it's 1 plus B, which is 6, multiplying e to the power, -0.7t. So now we know exactly what our function should look like based off the provided information. Well, that's our first portion down. Next, we're going to take a look at part B. Any questions at all, folks, on getting through this process? Definitely kind of a long process. Okay, well, now they have a follow-up question for us. This is the number of yeast cells after T hours has elapsed. Now they're saying, according to the model, what happens to the yeast population in the long run? Really a weird question. But these kinds of questions do get asked a lot, not just in our textbook, but in other texts like differential equations, any kind of modeling or engineering. When they say in the long run, they're asking us, what happens when we take the limit as T tends towards something of our function N, which we'll put in that full thing on the next step. But anyone knows what we should put here if we're talking about in the long run? It would be an infinity, exactly. We want to know what is the end term behavior. So we're thinking as time proceeds without bound, what is this population settling down on? So we haven't done a limit like this in a while. It's kind of turning into a review problem. We want to take the limit as t goes to infinity of 140, 1 plus 6 e to the power -0.7t. So that's our limit to compute next. The limit is not so bad, but it's tricky because we're taking t to infinity. We aren't using any fancy algebraic techniques. There's no conjugates, no factoring. It's all knowing what happens to the exponential function. So if you're faced with this kind of situation, t is going up to infinity, here's where I would look to in the notes. All the way back into section, geez, I think it was 2.6, yeah. We put down a table to help with crazy limits like those. And this is the table I would take a look at. If you're dealing with, say, e to the x, this is what your graph would look like. And the limit as x goes to -infinity is 0. The limit as x goes to +infinity would have been infinity. How many of these graphs do I have? I don't have a huge set of these graphs. The trouble for our problem is that's the wrong function, right? We don't have e to the t. We have essentially e to the negative t, well, negative 0.7 t. That means the whole graph really goes like this. If you want to plot y equals e to the negative x, you just flip it across the y-axis and it would look like that instead. So that curve right here is the one we need to think about when we go to take our limit. Any questions about those curves at the moment? Okay, let's take that graph. We're going to put it back into our notes and make it official. We're really just focusing on, after we hide that problem, this portion right here. If y equals e to the negative 0.7 t, its graph essentially looks like this. It will cross right at 1 when t is 0, since e to the power 0 is 1. The negative sign means it's dampening out as you go to the right, and it's exploding as you go to the left, like that, as an exponential function would do. That means this curve actually has a horizontal asymptote. Kind of hard to draw, but I'll just overlap like this, of a y equals 0. The minute you have a horizontal asymptote, you would know what happens to this limit. We can say limit as t tends towards positive infinity of e negative 0.7 t is the value of that horizontal asymptote of 0. So that whole thing, the short of it is, it's just gone as we take t heading off to infinity. In the long run, it doesn't contribute anything. And it's going to wipe out the 6 as we go. This turns into 140. 1 plus 6 times 0. So 140 cells, which if I take a look, yeah, it's the same value as A was as well. That was not a coincidence for this kind of function. So the long run behavior is it's going to settle down at 40 cells altogether. The initial amount of cells was 20. Well, any last questions, folks, on finishing off that follow-up question, part B? Okay, well, we did it. This one was kind of nasty, and it's pretty decent as a homework problem. This one could have been on the homework assignment. It would never, ever be a good one for an exam. I can't give you this much to work with on a single problem on an exam, but this information, once again, is the major takeaway. The exam too, and the final exam, if it involves this problem, it will involve this technique, taking information, breaking it down to a function evaluation, and breaking it down to a derivative. So if you can write a derivative and a function, you're in great shape for these kinds of problems. The homework is just a little bit longer since we have the time to consider how to work through this kind of stuff. Well, we did it. Any last questions before we try another one? Okay, the next one is not from cell biology like this one. It's not the geometry problems throwing in the lake we finished off last time. We're going to take a look at physics, which always makes me uncomfortable. Too bad we don't have Professor Barnaby with us, but we can still get through this kind of problem. It says here, the force F acting on a body with mass m and velocity v is the rate of change of momentum. And I'll just take their word for it. I'm not very great at physics, but I typed this out of our book verbatim, so I'm sure it's pretty accurate. So this is what they were saying. The force is the rate of change of mass times velocity, which I believe is how you would define momentum. So that's a weird equation. Usually we just say force is mass times acceleration, right? And here's a reason why we get to say that. I'm going to delete this in a moment, but just for a bit of explanation on this problem, if you say force is the rate of change is the d dt of mass times velocity, well, we think of mass as being constant, right? So we'll use a constant multiple rule and say this is mass times dv dt. But dv dt, if we look right here, that's the rate of change of velocity. The derivative of velocity is acceleration. You have to highlight that. So this will turn into mass times acceleration. The kind of formula we're used to, force is mass times acceleration, is just a little bit more familiar. So here's where the problem gets really, really weird. If n is constant, yeah, you really get that equation, the one we like. But mass isn't always constant. If you're going really, really fast, if you're really close to a huge source of gravity, you now have relativistic effects. And it says, in the theory of relativity, the mass will depend on your velocity. The faster you go, your mass is actually changing. It's no longer constant. It looks like this. Mass will be the initial mass, m naught, divided by this strange function down below, which does involve velocity squared. We divide by c squared, where c is another constant equal to the speed of light. So the faster and faster you go, the closer and closer velocity squared is going to equal to this right here. And we're going to get things that are just changing our mass as we change the speed. Ordinarily, for driving to work, the effect is so small as to be completely worth ignoring. But if you want to send a satellite out into space, maybe you're trying to work with cellular data, anything like that, you actually have to take into account relativistic effects, or else your GPS, your wireless, everything is going to break down. So this is really kind of weird. And they say force is really this. That's the equation we should be using if we think relativistic effects are important, launching satellites to other planets, things like that. So that's our goal. We're going to differentiate this function right here. Well, mass does in fact vary in this way, and they told us the answer. Our goal is to get that out as our response. So let's give this a try. First, any questions about the context on this one? Okay, let me delete this here, and let's try this out from the very beginning. We have force as the rate of change of momentum. So we'll start by writing force equals d dt of mass times velocity. And I put the multiplication in here because now mass is a function of velocity and velocity is a function of time. So right over here, that becomes a product rule. Those are both functions in their own right. That's really, really easy to miss here. So let's just emphasize. We have to use product rule. But now that we know it's the product rule, here's how this one will go. I'm just going to use the ordinary kind of derivative here. I'm going to take and copy first. Let's maybe copy mass. Then I'm going to differentiate velocity this time. So it'll be dv dt and go plus. Now this time I have to copy the other function. So I'll copy the velocity function v and differentiate the mass function. This will be dm dt. So ordinary product rule, copy one, differentiate the other, copy the other, and differentiate the first one. Does that look all right to folks on that setup there? Okay, looking through this, we can make a simplification right here. dv dt is acceleration. So we have acceleration right in this location. That's kind of helpful. It becomes mass times acceleration plus velocity times dm dt. Okay, so at this stage, let me color code this one. We need to calculate that derivative. Once it's calculated, we'll plug it in right where it's highlighted blue and keep on simplifying the force function f. Any questions at all, folks, so far? Okay, next thing to do then, let's calculate the rate of change of mass, dm, with respect to time, dt. But then notice we actually have a problem in calculating that derivative. Looking at the mass function, time doesn't emerge at all here. So we have to use the chain rule on this thing. And here's how the chain rule is going to go. We're going to use it in Leibniz notation, which is typical for an applied problem like this one, and say the rate of change with mass with respect to time is first dm dv. We have to differentiate mass with respect to velocity first, because it's first a function of velocity. Only velocity appears right here. But then velocity is an inner function in its own right. We must multiply by its derivative. And it would go like this: dv dt. So that's finally our chain rule in Leibniz form. The way you know you have it correct is they're not fractions, neither one of these. But if you visualize them as fractions, you would be able to cancel that denominator to that numerator, getting back dm dt. So we're getting there. That's the chain rule. And here's dv dt again. That turns into a. So now in the next step, it's dm dv times a. Well, that means the next thing that we have to do is go back to this mass function and really differentiate it with respect to velocity. We already have the a here, so we've accounted for the chain rule. So we'll be just taking an ordinary derivative, dm dv. Any questions at all first to this stage? Okay, so let's do dm dv. I'm going to put this one in a separate color, since I noticed this is kind of like a set of Russian dolls nesting into each other. Here's dm dv, and we go to calculate it. We're looking at this portion right here. Here, m naught is the mass of the particle at rest, or in other words, the initial mass. That value is actually constant. When there's no movement, relativity says nothing about your mass. It just is what it is. So this m naught is constant. Here, the c is the speed of a light, so c is also constant. The speed of the light in a vacuum is unchanging. So when we go to differentiate this, the only thing that varies is v right down below there. That means if you wanted to, you could take another approach on this function. You could say mass is equal to m naught divided by 1 minus v squared over c squared to the power of 1/2. That'd be a good start. And if you really wanted to, you could also say it's equal to m naught times 1 minus v squared over c squared to the power of negative 1/2. So all I've done here is taken the square root, made it an exponent, brought that exponent up into the numerator, and it looks like this. Reasons for doing that this time is it's a huge time savings. If you differentiate this directly, it's a quotient rule with a constant on top. So it's a lot of writing, but you would still have to differentiate that square root. It's still the chain rule, no matter how you look at it. Written in this form, same chain rule, but no quotient rule. That's a real time savings this time. So let's try differentiating it in this form right here. That sound right to folks? Okay, so differentiating that thing, coming down below here, this is now equal to, or let me do it down here just so it's not getting too busy. dm dv is now equal to, coming up to where this is, m naught is a constant, so we'll just write it in. Since it's multiplying, it doesn't go anywhere. Next, we have two functions. Over here, that's our outer function we'll handle first. And inside, that's the inner function of v that we'll do second. So this derivative is going to look like this. 1/2 comes down as a coefficient. For that inner group, we subtract 2/2, thereby subtracting 1. It's now to the power of negative 3/2. Then multiply by the derivative of whatever is inside, the inner function 2. So that's our setup through chain rule. Does it look all right to everyone so far? Okay, if we're all happy, take your inner function 2, goes in both of those placeholders. 1 minus v squared over c squared here, and 1 minus v squared over c squared here. And I notice I did make one big omission. Really good idea. Each time you do these kinds of things, product rule, quotient rule, and chain rule, don't forget the primes, because I mean, it would be easy for me to not differentiate it on the next step because I didn't see the prime symbol. Okay, so at the moment, this is our whole goal right here. crank out this derivative. We have got one more piece to go. And this one is no longer chain rule. In fact, we can write this down just a little bit nicer. For differentiating, this is not the nicest format. It just looks cleaner if you think of it as a 1 minus 1 over c squared times v squared. The reason for that is there's no fancy rule right here. 1 over c squared is another constant, and when you differentiate, you just get a 2 coming down. So that'd be the better way to visualize it. So now in the next step, we can start consolidating things. We can call this a negative m naught. That 2 right here, I'll throw down into a denominator. For that exponent, we can force it positive, thereby throwing the whole thing in the denominator. Now it has power positive 3/2. And this derivative, when we crank it out, I'll just put it to right inside here, multiplying it inside the numerator. So it's going to turn into, get a longer numerator. First, that constant is not multiplying, so it goes to 0. We'll have a negative 1 over c squared times 2. When we differentiate the v squared here, we'll have negative 2 over c squared, v to the power of now a 1. So that's what would happen to that stage. So just visualizing this, what happened was 2 came down. I wrote it right inside where the 1 was. So 2 over v squared. New power v is just a 1 now. Any questions, folks, to that stage? Yeah, go ahead.
Why would the constant be 0? Why would that term be squared? Why would that not be squared?
This portion right here, only because it's multiplying. Think of it sort of like this whole thing. For a nicer looking function, it could have been like a y equals 3 plus 5x squared, for example. The 3 is the 1. The negative 1 over c squared is a nasty constant. Think of it as like a 5. And instead of v squared to x squared, here y prime would be 0 here. 5 would stay in position only because it's multiplying. Then we would use the rule here for the power rule, 2, and then an x to power 1 to get a 10x. Yep, you bet. But here it just looks nasty, and that's kind of the trouble with this work. If we get too used to x's and y's, we miss the patterns when it can no longer be x's and y's, like in an applied problem. But if you can write down an example like this to conflate the two, sometimes it helps out a great deal. But other questions so far? Okay, next thing that can happen to this, there's all sorts of weird things happening to this function. But there's a quick cancellation. There's 2 negatives here, so you can convert those to positives. I'll visualize it like this, canceling them off. This 2 in the denominator can cancel that 2 in the numerator, so they're gone. And the next thing we'll write is, well, for the numerator, the only survivors are m naught and v. Where did c squared go? We can now force that into the denominator right over here, multiplying the 1 minus v squared over c squared to the power of 3/2. So that's where dmdv would end up. Well, where does dmdv go? It's this portion right here, which gets tied with dmdt, which goes over here. So now we have to start unwinding everything all at once. But we have all the derivatives, so this is the nuts and bolts so far. Any questions so far, folks, to this stage? Okay, so now the claim in the problem is that if something is moving really fast, here is the actual force acting on it. It's still the rate of change of momentum, but whatever we're doing on our paper, it has to come out like that. So let's put it down here just for a moment. That's our goal right there. Now we have to decide how to unwind this. Let's see. I guess we could just restate the force function up here. Force on the second page is now equal to, right here when it says mass, already that's something we need to copy down as well. Let me grab this. Let me attempt to copy this down. Okay, I think I've got it. Just gonna put it here temporarily. And now I'm at this stage. So I'm writing down the force on this portion. I put down, well, I don't want to put down M just yet, because M is really this. That's why I copied this down below here. See if I can move that. There we go. So where M is, I'm going to copy M naught root 1 minus V squared over C squared. Then we're multiplying that by A. So it'll be times A right here. Next, we have to add on V for velocity. And now we multiply that by dm dt. So now we're unwinding. Down here, dm dt becomes this, dm dv times acceleration. I'm not sure how much we want to put in at once. Let me start by just putting this so we can see how everything is tracking through. So where dm dt was, I'm just putting in this whole thing, dm dv times A. So I think we can eliminate that now. I need to still make another substitution. And that substitution will be for dm dv. It came in as all of this stuff right here. So we need to replace it in that location, following the green color coding. So on the next step, it's m naught times A. In the denominator, well, we don't have a square root in this denominator, so we might have to do something with this. I'll just call it 1 minus V squared over C squared to power 1/2, and let it sit like that for the moment. Then here is, I'll take plus A V. So I'm just taking the acceleration velocity together, and now it multiplies. Here's our big substitution, dm dv, which is right here in green. It's another mass, initial mass, so m naught times v, divided by c squared, 1 minus v squared over c squared, to the power of 3/2. So it finally is all inside here some way, somehow, but some way, somehow, it has to turn into that force function down below. There's still work to do. I believe we have the right derivatives. This is tricky. If we're missing something, we'll find out immediately when we don't get to that final form. But you want to see what the next step should be to try to get to this end result. I mean, there's no more derivatives to calculate, right? There's nothing that apparently simplifies or cancels or combines. But if you have two fractions, you can at least try adding up the fractions and just see what happens. So that would be my last thing to try. To get the fractions to add up, well, I'm missing c squared right here, so let's input it. I'll use this color for finding the least common denominator. So here's a c squared. It has to go below and above. Next, well, we have power 1/2 here. It needs to be power 3/2. So we can multiply by 1 minus v squared over c squared, just to the power 1. I mean, that's really power 2/2. These exponents would combine to give us 3/2. So up in the numerator, 1 minus v squared over c squared, it's to power 1, and I'll just leave it like that. I only wanted the 2/2 to show those two combining. Well, it's getting better. Let's see what happens next. We have the least common denominator at this stage, so we can say this is equal to 1 overall fraction. Probably doesn't have to be that big, but for good measure, here's our fraction. The denominator will be c squared, multiplying 1 minus v squared over c squared. Multiplying those two together will be power 3/2. Checking on the green fraction denominator, yeah, it's exactly the same quantity, so we really have the true denominator. And it does match up with that denominator, so that's good evidence we're at least on the right track, aside from c squared needs to be eliminated somehow. Now, next for the numerator, we're just going to add all this stuff up. We can distribute as we go and take all of that times 1. It would become mass, initial mass, m naught, ac squared. Then make it multiply this. That's a nicer multiplication because this c squared here will cancel with that c squared in the denominator. All it's going to leave is minus m naught a v squared. I'm going really slow at this stage. For me as well, this is kind of tricky. And if I miss any tiny thing, there's no hope of getting that right expression down below. Does that look right to folks on that distribution? Awesome. Then last thing, this can multiply into the numerator, and then we'll add the numerators together. So it's a plus a m naught v squared. So let's see here. Our numerator has, hey, it has something good for us. The terms are kind of mixed up, or the factors of this term and this term, but they both involve a, m naught, and v squared. They have opposite signs. So those are gone. We might actually be in business with this one. So the next step we can say is, after cancellation, it's m naught ac squared divided by c squared times 1 minus v squared over c squared to the power of 3 halves. And in this form, a new cancellation happens. We can eliminate those c squares, so they're gone. And we end up at an answer that, I mean, it's still mysterious. The physicists assure us this is the right answer, but it's m naught times a 1 minus v squared over c squared to power 3 halves. Double checking, that is what we were going for. So pretty tough problem. Any questions at all, folks, on getting through this one? Okay, so apparently if you are going really, really fast, a significant proportion of the speed of light, the force acting on you is not mass times acceleration any longer. It's initial mass times acceleration divided by that. So some construction that combines your velocity along with the speed of light to these weird algebraic forms. Somehow they verified this and it at least works. I mean, cell phones work. So I trust the physicists. Amazing how they come up with that stuff though. Any questions at all getting through this one, folks? Awesome. Well, we're at the part of the day where I think we've solved every single question on this set of notes. So what I want to do in case we finished early is let's take a look at the upcoming assignment. It's only the 2 sections, 3.6, 3.7. And let's take a look at the 3.7 exercises. There's various different kinds of problems on here. And just to give you some help on each one of these, on number 11, it says a rock is thrown vertically upward on a surface with Mars with 15 meters per second. Its height after t seconds is this. What is the velocity after 2 seconds? You're really just differentiating and putting in 2 seconds. Was the velocity of the rock when its height is 25 meters? For this one, what you would need to do is put in 25 meters for the height and find the times when it actually hits 25 meters. You'll get 2 time answers, put them back in your velocity function, and you'll be all set on that one. So this one's not too bad, but still, it's one of those problems where you have to work on it, try a couple things, maybe backtrack, and then you get through it. 22, well, this one's another physics kind of problem. Maybe let's turn back to that one. And 23, this one is more from the medical field of, this is the time required to complete dialysis with a certain amount of concentration of urea in your bloodstream. So I'll leave it up to the class. Which one do you want to look into further? Urea concentration in dialysis? Something with the force of gravitation between 2 objects, or something dealing with a rock being thrown vertically? The dialysis? Good choice. It just looks terrible. So let's give this one a try. I won't have time to complete it. I want to leave the end completion to you, but I definitely think we can get some good work getting this one started. So I'll just put it right here on the next page of these same notes. And we better now actually read the question, see just what in the world is going on here. It says patients undergo dialysis treatment to remove urea from their blood when their kidneys aren't functioning properly. It's a pretty terrible treatment, so our hopes is to never have this kind of procedure. What they do is they're going to divert your blood from the patient through a machine. It's a big old machine. They'll filter out the urea, and it takes a really, really long time. You have to do it a lot. So knowing how long it's going to take to run this procedure is very, very important in the medical sciences, just for scheduling dialysis treatments. Here, the urea concentration C is positive, but that's not necessarily a constant. It looks like that's what varies in this problem. C is the independent variable, and T will be the dependent variable on this one. We want to predict time based off how much urea C you have in your bloodstream. So that's the equation. We need to calculate the derivative and then interpret what its meaning is going to be. So when we go and give the interpretation of its meaning, it's not going to be like this one. Sorry, let me get to the right spot. The interpretation is not going to be like this. Here, we didn't just take a derivative. We input a value and got -4 centimeters per second. Our interpretation was really on that quantity there. But on the current problem, all you're going to do is take a derivative and not evaluate it at all. So just say generically what the derivative represents using the context. It's a really fast kind of interpretation, nothing too major. But first things first, it's a logarithmic function, so you do get a little bit of help on this if you use properties of logs. There's not a lot of properties we can use, but you can say t equals the natural logarithm of 3c plus the square root of 9c squared minus 8c. Because of the division bar right here, we can also say minus the natural logarithm of 2. It's not a huge time savings, but it does save us a little bit of time on getting through this one. Well, right here, this is what makes a problem hard. If that was a multiplication, you could use even more properties of logarithms. You could make it natural log of 3c plus the natural log of a half, then 9c squared minus 8c, and the whole problem would be really quick. But we can't do anything with the plus here. There is no property of logarithms. We just have to live with what's there. And another thing that's tricky about this one is if we go to take this derivative, it's going to be the derivative with respect to urea concentration, so DDC, of that right here, natural log 2. Any volunteers for what that should come out as? Exactly, this must be a 0 because natural log 2 is a constant. Even if we said ddx, ddt, any derivative here must return a 0. And you could check it out. Natural log 2 is it's a positive number less than 2.7. So it goes to 0 immediately. That means when you go to differentiate this thing, you're only focusing on that portion. But it's a chain rule immediately when we go to differentiate that. Natural log is the outer function we'll do first. And that entire input is the inner function we handle second. So now we're ready. We've done all of our analysis. We can take this derivative. You could call it t prime, no harm done. If you like Leibniz, you can call it dt, dc. In this format, it's reminding us that t is the independent variable and that c is not constant this time. It's just like x. We're differentiating with respect to that independent variable. We take the derivative of the natural log, and that one's always a nice derivative. It goes like this. So that handles the natural logarithm derivative. Because it's a chain rule, we'll also go times another derivative like that. Then standard procedure, take your entire inner function, put it in both of those placeholders. So 3c plus root 9c squared minus 8c will go here and here. 3c plus root 9c squared minus 8c. Well, we're getting through it, But this derivative right here, it's just as involved in a certain sense as the original one on the first line. This is what's kind of a good thing to mention when it comes to applied problems. They're just messy. A problem like in section 3.4, 3.5, 3.6, they had no context, so they're all kind of clean, easy to work with mathematical problems. But anything that's applied, it has a tendency of getting messy like this one. I mean, this one was really messy, the one right above. So that's part of the skill in these problems as well. No matter how nasty it gets, just keep on cranking through the computation and you will always get lots of partial credit, even if you did make a tiny mistake somewhere along the way. So let's keep on going with this one. Let's see how far we can get. The denominator is completely settled. Nothing's happening there, so we can leave it as a 3c plus the root of 9c squared minus 8c. When we calculate this derivative, we can multiply the input into the numerator like we typically do. But first, it's the sum rule. A would see what the derivative should be where the red dot is currently. Yes, absolutely 3. I thought it was a constant for a second. I was about to say 0, but no, c is a variable. It's like differentiating 3x. Turns into just a 3. Good call, folks. Then we need to do that derivative. Well, that one's not so great, right? That's another chain rule in the process. So we'll go plus and do a whole new analysis on this thing. The square root function, that's our outer function we have to handle first. And the polynomial, 9c squared minus 8c, we'll do second. Now, if you call this power 1/2, that's not a bad thing to do. The 1/2 will come down, new power is negative 1/2. You can throw everything into the denominator, or you could use this formula. Derivative with respect to x. Yeah, let's leave it as x, just a general formula if x was in the problem. For root x, always turns into 1/2 root x. That was a formula we stated when we were dealing with this derivative. Because they're so similar, they kind of go together. But this happens so often as a derivative, it's a good formula. And it'll help right here as well. So back to the drawing board on this thing. Differentiating the square root function gives us this format. It'll turn into 1/2 square root, a placeholder here. Then because it is a chain rule, we have another derivative that goes right here. So we take the inner function, this time it's 9c squared minus 8c, put it in both of those positions. And we're pretty much well on our way with this one. All that's left to do is take that derivative, you can put it into the numerator, simplify this as much as you feel like you would like to simplify it, but you should never take loads and loads of steps simplifying. It's not a bad thing to do, but if you feel like you're not doing calculus, you're doing mostly just algebra on your homework, you could have taken less time on the simplification. On this one, you could simplify a pretty good amount by also multiplying. This is optional, but if you want to make it look like the back of the book, you could also multiply by root 9c squared minus 8c, not a conjugate this time. Its purpose is to clear that denominator by the red dot. So if you multiply that through, it's going to clean it up a pretty good amount. So last things, take the derivative, multiply this through into the group right here. It'll simplify like you expect to see it in the back of the book. And then just say what this is representing as a quick interpretation. Any questions at all, folks, on the setup for this one? I guess it's a setup and then a couple of extra steps. Okay, well, I appreciate everyone's hard work. These are kind of challenging topics. Next class will be in section 3.8, and it'll be about exponential growth, exponential decay. So it's a lighter section, more familiar topics. It also has Newton's law of cooling, but that's not too far of an extension from those other type of topics. Well, I think this is a good stopping point for us, folks. So if you have any questions, I'll be happy to help out. Otherwise, have a great weekend. Be right back. Oh, sorry, you're just handing it. Gotcha. You betcha.
But.
For me, it's usually.
So I want to go on my. No, it's. They're going to. Yeah.
Yeah, absolutely. That's what I hear. Yeah. So we have cosine x by this part. X, y, you have to multiply by the derivative of x, y. So both x and y are in parentheses. If you're using Leibniz notation, the dydx should go in front. If you're using a prime, the prime would just be right there. It would just be a prime on the parenthesis, not the y itself.
Oh.
So essentially what's happening is the sine is the inner function, the differentiate is the cosine, and you put in the input, and the input is the derivative by 2.
Okay, and then equals.
And same kind of thing with this one. Yeah, exactly. So you just get x prime, which is 1, and then y prime, which is y prime, nothing happens. But this one is 1 plus 1, it'd be a 1 plus y prime. Does that make sense on that one?
Yeah, please, this is that's a good nothing. Well, please, there's a word there, you know, but.
Yeah, exactly. The point is the challenging one. That only have to use a positive. So if the derivative of x times y plus x times the derivative of y. Yeah, exactly.
And so now it's just 1. And y plus x. 2 times 2y.
Could be a y prime.
And
So this whole thing goes right there, still in parentheses, and cosine x y will multiply through. Similarly, this right here will multiply through those two. So now you can have it all extended, and the goal is just to solve for a y.
so then I have cosine x y there. And then cosine x y times y.
Oh, actually, it's because of the times, it would just be, this is really just a y altogether, right?
Oh, yeah, yeah.
So it would just be y cosine x y.
Times. And then times the, when I saw the time on that one. And so, times x y is just x.
Well, it's multiplying that whole thing.
Right.
Yeah. Oh, but with the parentheses here, you want to drop that parenthesis because this one and that one.
So,
Because your prime is just affecting y this time.
so. You just say that again.
Here, it's really just an x. So you copy x there. Because you don't need parentheses around it, just an ordinary x.
And this one, we drop the parentheses as well and just call it y prime. The trouble though is, the reason why it has to be written this way is because if you write it that way, it's a product rule again. But you already compared it, yeah, exactly.
And then negative side. I do it to this one.
Yeah, now you're distributing it to that group.
With, and white.
Or not quite, what happens is, first this multiplies to a one, so it's just sin x plus y.
Yeah.
But then on the next step, this multiplies across plus and attaches to the y prime.
Wait, if you make my.
Oh, good call, I didn't see that.
Y prime, is just one.
It would be a y prime. Yeah. So that's the thing that you have. Now your goal is to get y prime on one side, factor it out and divide by whatever it is.
So both of these would go on one side, and both of these would go on one side,
Yeah.
and then divide by this.
Whatever you, yeah.
Okay.
Any questions on this?
Yeah, that's definitely.
Gotcha.
Because I just don't understand it, I think I got this one, but I don't.
Gotcha. What was the question on this one?
But one second, what was, this is section.
3.4. So change what we got.
This was, that's obviously different from. And I thought, it doesn't keep the same, what we do. That's why I do.
Gotcha. But I think the first thing you have to do on this one, because it's e negative x times cosine squared, you have to use a product rule to start this one.
Yeah, I don't know. I didn't know.
Well, the product rule is going to do that structure where it's the derivative of the first thing, copy the second thing, and plus, and then zero. Exactly.
So technically, well,
But you have to have your x squared inside this. Gotcha. So this is the set of the product rule. You just need to put a prime on one and a prime on the other. Then you differentiate that one, differentiate this one, and result. You said negative. Not quite on this one. The derivative of dx is just dx. But this one here includes the negative x, so you also have to use the change in amount.
Just E and F.
It would be more than that. If you were to differentiate negative x with a chain rule, let me put on the board what it would look like. So that one portion of your problem right here, e negative x prime will turn into, first we have to say that that's your outer function. And the negative x right here would be your inner function. So upon differentiating this by the chain rule, you would differentiate e to the x essentially first. It would look like that.
Basically,
And then multiply by a derivative like this.
so basically, the same thing I did with that square root.
Pretty much, yeah, that was the chain rule as well. This input, the inner function would go here.
And that would just become one or negative one because x of then because it becomes nothing, it just becomes one.
Yeah, this turned into a -1, so here's that negative sign. And then e negative x. So that derivative would turn into negative of e negative x.
So literally all it is would just make it negative.
Pretty much, yeah, exactly.
Okay, then I was gonna say that x affects e and makes e negative.
Gotcha.
And then because that cosine is left alone, that is left alone, that cosine will become sin because it's derivative.
Mhm.
So it would just be sin of that, so you've got cosine and sin,
But your sine, or let me take a look again.
this would become sin.
If you're differentiating.
It's gonna do the exact same thing, that's what.
Yeah, this one's got another chain rule. So yeah, derivative of cosine turns into negative sine times a new derivative like this. The thing that goes inside this time is x squared.
So we can see there. And then x squared is just gonna be two x,
Exactly, yeah.
so it's just two x that goes in front of the sin.
So you have a negative two x sine x squared.
So
Questions over here?
Would that look,
Let me take a look. So y cosine xy, so that's this multiplying here, cool. Then here to here, cosine xy prime. Then here to here, that looks good. Back to that, the y prime, that looks awesome. So now we're getting everything with y prime on one side. So
and
putting
then
it to the
only
left.
take out the y part, right?
Yeah, exactly.
So then I leave that x in there.
Mhm.
Okay,
Then you divide by all the stuff that remained, cosine xyx, my sine xy, y cosine xy. I think you got it. That looks
okay,
great.
that makes a lot more sense now.
Awesome.
Okay,
basically, we just have to look.
thank you.
Yep, you betcha. Negative e negative x. It would be a multiplication right there, coming from right there. So still multiplying.
And because it's a cosine, you can't really do anything unless you smack it really right in front of it.
What do you mean?
Well, because every time this means this goes right in front of it.
Yeah, essentially. You can leave it blank even if you wanted to. It just couldn't be a plus sign.
And then that's just negative because two x minus two x of sin of x squared.
Yeah, exactly.
Okay. And this one is basically the same thing.
It is, but when you go to write out the derivative on this one,
You have to do t and sin separate.
yeah. you
Like
have
I did,
another product rule right
like I
there.
did with the other one, it was the same.
Mhm.
One other one, basically, it's gonna end up similar to the same answer, it's just, it's derivative from,
Yeah,
so I have to derivative from E first.
so if you were to write this one out, take its derivative, it would go like that, like you're saying.
First, the same thing up there, and then it's how you sell.
Yeah. And then,
So if you, because that, the first P ends up in the same. That's it, it doesn't have to do that.
yeah, this is left alone.
So what would happen technically is just cosine, because that is like one, to make it that much distance. Because one times two is that. It would, and then there would be cosine.
But there's an extra problem on this one.
Oh, I have to do it further.
It's a product
So
rule.
I have to do the T.
Yeah, exactly.
Well, what do we do?
This one, it would be a positive, derivative sign is a
So
positive.
then it's literally just gonna end up with E squared plus A.
There should be a t squared though, when you go to differentiate this.
Oh, yeah, well, yeah, actually.
Yeah, exactly.
Because that first, the first thing gets derivative is like one, and then then you got T plus one. and
Yeah.
that's plus the thing.
Or,
Because this would become one, well, then you times that, so then it would just be this,
it'd just be a sine t for the first term.
and then it would just be cosine plus T, so it basically just look like this, but make it different.
Exactly. Okay, then cosine plus t, but it should be cosine times this.
Yeah, then it was like,
Yeah, exactly. What with the cosine function?
the ten. Then it would be plus. Yes. Oh. Then plus.
Yep, that sounds great. Does that make sense to you, how they're coming together?
Yeah, and the biggest problem.
What's going on with this one?
I got this one.
Gotcha. So the next thing you have to do is solve for your dy dx.
I'm not quite sure how to do that.
You need to put your dy dx's, every term that involves it,
So
on
basically-
one side of the equation.
So I either take all the x, well, what about this one, this is the height.
Mhm.
So what I do?
Well, there's no y prime on this one,
So everything that doesn't have a dy dx,
Mhm.
it's, has to be on one side. Everything that does have a dy dx, it has to be on the other side.
So technically these two,
Are you gonna keep them on this side
so
or?
everything right here,
Mhm.
could get minus and we go here.
Yeah, exactly.
And then that's just it.
No, then you need to factor out dy dx.
So, Then. Um,
Oh, so next you have to factor out dy dx from those terms and divide by the thing that remains to the other side.
How do I do it?
How to factor the dy dx?
Yeah.
You'll go dy dx. Then after you factor it out in this form, you would copy in the 2y. In fact, it essentially divides out when you factor. It leaves the 2y, here it leaves 8/2. And the way to visualize it is, if you went backwards, you just distribute this way by the distributive law. So we're just reversing distributive law when we factor it out.
So what was
Then you divide this into your right-hand side. And you solve for dy
So
dx at that
basically-
point.
all of this, everything right here is divided by this.
Everything, you're saying everything right here is, yeah, exactly.
So technically, all of this, right here, minus two right. That's the answer.
Yeah. Well, it's,
Technically, all of this right here is the answer.
well, I think it's wanting you to do more because it's saying something
Oh, yeah.
3-1.
3 and 1, so the 3 is the as x, so technically, if I really wanted to, I can take everything that's x, times it by 3.
Exactly, yeah.
And
Or
that is where I
replace it
can
with
whip out the
3.